Have you ever just stopped and looked around? I mean, really looked at your desk, the air you're breathing, the glass of water next to you, and just wondered, what is all this stuff, really? Well, today we're going to peel back the layers of reality itself. Let's get into it. It is a massive question, right? But believe it or not, the answer starts with just one simple word. And that word is the key to understanding everything, from a solid rock under your feet to the invisible gas all around you. And there it is. Matter. That's the big secret. If it has mass and takes up space, it's matter. So your phone, that's matter. The coffee in your mug, matter. Even the air filling up your room is matter. It is the fundamental stuff of our entire universe. Okay, but just saying everything is matter doesn't quite cut it, does it? To really get what's going on, we have to look closer, like way, way closer. We're talking about the particles that make up all this stuff. And trust me, they've got some pretty incredible secrets. So, what you're looking at here is a hidden world of nonstop action. These particles are unbelievably tiny, but they are never, ever still. They're constantly vibrating, zipping around, powered by something scientists call kinetic energy. And get this, the more you heat them up, the crazier their little dance gets. They can even wiggle past and mix into each other, which is a process called diffusion. And the only thing stopping them from flying apart is this force of attraction, kind of like a cosmic glue holding it all together. So this constant dance of particles and how strong that cosmic glue is gives us the three main faces of matter that we see every single day. You know what they are? Let's break them down. This table just lays it all out so clearly. Think about a rock. That's your solid. It has its own shape, its own volume, because its particles are packed in there super tight, barely wiggling. Now, picture water. As a liquid, it'll take the shape of whatever glass you pour it into, but its volume stays the same. The particles are still close, but they've got enough room to slide past one another. And finally, gas. Imagine the air in a balloon. Its particles are so far apart and moving so fast, they just expand and fill up any container you put them in, no matter the size. Now, that huge space between gas particles gives them a kind of superpower, compressibility. You can squeeze an absolutely massive amount of gas into a really tiny space. And this isn't just a science experiment. It's exactly how we get compressed natural gas, or CNG, into a small tank to power a car. It's a perfect real-world example of these particle properties in action. All right, so we've got solids, liquids, and gases. But here's the cool part. They don't have to stay that way. Things can change. So now let's look at how matter pulls off its great transformation from one state to another. You want to know the secret ingredient for changing states? It's energy, usually heat. When you add heat, you're giving those particles more kinetic energy. They start vibrating faster and faster until they break their bonds. A solid melts into a liquid, which can then boil into a gas. And if you cool things down, the whole process just reverses. It's this beautiful, simple cycle. But wait, here's a little mystery for you. If you stick a thermometer in a cup of melting ice, you'll notice something weird. Even though you're adding heat, the temperature stays locked at a perfect 0 degrees Celsius until every last speck of ice is gone. So where is all that heat energy going if it's not making things hotter? And the answer is latent heat. It's hidden energy. That heat you're adding isn't trying to raise the temperature. No, it's got a much bigger job to do. It's being used to literally break apart the rigid bonds holding the ice crystals together. Once all the bonds are broken and the ice has become water, then the temperature can start to climb again. It's the secret energy behind the transformation. And of course, scientists have a whole vocabulary for these changes. Melting is officially called fusion, freezing is solidification, but check out that arrow at the bottom. That shows us that sometimes matter can skip the whole liquid phase entirely. The most famous example of this has to be dry ice. It's just solid carbon dioxide, but at room temperature, it doesn't melt into a puddle. Nope. It turns directly into this awesome, spooky-looking gas. That jump from solid to gas is called sublimation, and the reverse, going straight from a gas back to a solid, is called deposition. Okay, so we've covered the states of matter, but let's zoom in from a different angle. When we look at something like a glass of lemonade or a scoop of dirt, is that just one thing? Or is it actually a jumble of different things all thrown together?
This right here is an absolutely crucial difference. Think of a mixture like a salad. The lettuce and the tomatoes are just physically hanging out together, you can still pick them out. But in a compound like water, which is made from hydrogen and oxygen, a chemical reaction happens that creates a brand new substance with totally new properties. The recipe is always fixed, and you can't get the hydrogen and oxygen back without another chemical reaction.
And even mixtures come in different flavors. A solution, like lemonade, is perfectly mixed all the way through, what we call homogeneous. A suspension, like muddy water, has big particles that you can see, and they'll eventually settle to the bottom. And then you have the weird ones in the middle, colloids. Things like milk or fog. They look evenly mixed, but their particles are just big enough to scatter light, which is why you can't see through them. So we've gone from the big picture of matter to its different states to how it all mixes together. Now, it's time for our final and deepest zoom in. What is the smallest possible piece of matter? What's the ultimate building block of everything? For thousands of years, this was purely a philosophical question. Ancient Indian and Greek thinkers dreamed up this idea of an ultimate indivisible particle. They called it parmanu, or atom. But it stayed just an idea until the 18th and 19th centuries, when scientists like Lavoisier and Dalton started doing real experiments and turned this old philosophy into a real scientific theory. And this is what John Dalton came up with, and it was absolutely revolutionary. He proposed that everything is made of these tiny particles called atoms, and that these atoms were the fundamental, unbreakable building blocks of reality. He said all atoms of an element, like gold, are identical, but they're different from the atoms of another element, like oxygen. This simple theory became the bedrock of all modern chemistry. So Dalton's theory basically defined the atom as the end of the line, the smallest possible piece, something that could not be broken. But what if he was wrong? What happens if you take this supposedly indivisible particle and you actually try to split it?